Today's lesson is on angle measures and segment lengths. We got 3 theorems and a definition or two to learn, and then the rest of it is just working some practice like we like to do. And I forget to say it often, but I do like you to go back and write a summary and fill in this essential question right here when you get finished. I think you'd find it helpful if you'll do that. So here we go. What is a line that intersects a circle at 2 points? It's called a secant. A secant to a circle. So here we go. AB, line AB is a secant to that circle. Now, we also know that segment AB is a chord, right? And sometimes we will call those secant segments. So a secant segment and a chord are the same thing. Generally, when we refer to a secant, we are talking about a line that intersects a circle at 2 points. So let's see what these new theorems are that have to do with secant lines to circles. All right, the measure of an angle formed by 2 lines that intersect inside a circle. So these are 2 secant lines, but it could also be, this theorem would also apply to 2 chords that intersect inside a circle. The measure of the angle is half the sum of the measures of the intercepted arcs. So you can see that angle 1 there, its measure is 1/2 of x plus y, intercepting inside the circle. Okay, now, the measure of an angle formed by 2 lines that intersect outside a circle is half the difference of the measures of the intercepted arcs. Okay, so let's commit this to memory. If the segments or the lines intersect inside the circle, then the measure of the angle is going to be half the sum of the arcs. If the intersection of the 2 lines or segments is outside the circle, then the measure of the angle will be half the difference of the intercepted arcs. All right, so the best way for this to start to make sense to us is for us to do some problems. So here we go. What is the value of each variable? Well, we've only got one variable here, and if we're going to apply one of these theorems, we got an intersection outside the circle here, so that we know the measure of the angle. I'm just going to leave it angle for now. The measure of the angle is half the difference, right? If the intersection is outside, so the bigger arc here would be W. Smaller arc is 110. And I know the measure of that angle is 70. So 70 is 1/2 W minus 110. Multiply both sides by 2. I'll have 140 equals W minus 110. Therefore, W is going to be 140 plus 110, which would be 250. All right, now it would have been very easy to do that without using this theorem, because we know this arc here is 110 and the other arc is the entire rest of the circle. So we could have done that very simply by just saying 360 minus 110, but we're supposed to be practicing our new theorem, so that's what we did. Okay, what do we got in B? Again, we have an intersection outside the circle, so we know that the measure of angle, we're just going to call it y, although that's not really the angle's name, but that's what's there, so we'll call it that. The measure of the angle is 1/2 the difference of the 2 arcs intercepted, 110 minus 30. So that's equal to 1/2 of 80. And so y there is going to be 40. Okay, this is easy, right? All right, now what do we have? In C, example C, we've got an intersection inside the circle, and we got to remember that to get the measure of this angle, it's going to be half the sum of the intercepted arcs. So we already know what the measure of the angle is. It's 35 degrees. It is 1/2 the sum of the intercepted arcs. I'm going to multiply both sides by 2. 70 degrees equals x plus 30 degrees. Therefore, x is going to be 40. All right, simple as that. Okay, now let's see what we have here. For a given point and circle, the product of the lengths of the two segments from the point to the circle is constant along any line through the point and circle. Oh my gosh, what on earth does that mean? That sounds really confusing. Okay, I'm going to tell you something so that it's not going to be confusing at all. It seems painful, right? Seems painful? Does it make you want to say, ow? Well, I hope so, because that's what's going to help you. Ow equals ow. Think of ow, ow. Oh my gosh. Okay, what does this ow, ow business mean? It means the outside times the whole equals the outside times the whole. And that's all you got to remember here. You don't have to worry about what all those words mean. We're going to do outside times the whole equals outside times the whole. That actually, I got a little ahead of myself here. That actually applies for cases 2 and 3 here of this theorem. Case 1 is much easier, right? If I've got two chords intersecting inside a circle, I know that part of one times the other part of that one equals the part of another times the second part of the other one. Okay, so let's do this example here, and then we'll get to some ow, ow examples. Okay, let's see. JN and KM intersect inside a circle. So X is what we're calling LN here. So we know part times part equals part times part. Okay, so 10 times X equals 8 times 5. That is all that we mean by part 1 of this theorem. So X is going to be 40 divided by 10, or 4. Okay, so that is easy. Okay, but now comes the ow part. Outside times the whole equals outside times the whole. So the outside here, let's start here. The outside is 12. What's the whole thing there? X plus 12, right? X plus 12 is the whole length, and that equals the outside of the other secant, which is 15, and the whole thing is 9 plus 15, which is 24. Okay, now I'm not going to go ahead and distribute this 12. I'm going to divide both sides by 12. I think that'll make my job easier. 15 times 24 divided by 12. Ooh, yeah, I like that, because 12 goes into 12 one time, it goes into that 2. So I got X plus 12 equals 30. Therefore, X is going to be 18. So that chord BC is 18 units long. Ow, ow. Outside times the whole equals outside times the whole. All right. Let me see how many more. Ooh, not many more. We'll just do these together. You'll have plenty to practice in class tomorrow. Find the values of X and Y. Okay, well, we're going to start on this right circle here, and we're going to use ow, ow, outside times the whole. And oh, let me go back up here for a second. You may be looking at case 3 here. Let's look at case 3. You see here, we don't have any, the outside is the whole thing. This tangent here is the whole thing. So when we say outside times the whole, that's actually T times T. Okay, outside times the whole, the outside is the whole. That's where the T squared comes from. And the outside down here is Y, and the whole thing is Y plus Z. Okay, so when we have a tangent, it's the outside and the whole, so we got to remember that. Okay, so let's look again at this circle on the right. So the outside times the whole, so that would be 10 squared. I don't know why my pencil keeps failing to work. Hold on. So 10 squared equals the outside over here. The outside over here is 6, and the whole thing is X plus 6. Okay, So I got 100. There goes my pen again. Okay, let me try this again. 100 equals 6x plus 36. 100 minus 36, 64 equals 6x. So x is going to be 64 sixths, which is 32 halves. Ooh, I know we hate that, but that's the way it is. Okay, left circle. Hey, why don't you pause and do that one? I'll have the answer up when you get back. Hey, guess what? I missed that. It should be 32 thirds. You knew that though, right? 32 thirds. Okay, so when I come down here and put in the right number, outside whole, so the outside times the whole is y squared, and the outside times the whole in the other one is 6 times 6 plus 32 thirds. And when I do the distributive property there, I get y squared is 100, therefore y equals 10. Y equals 10. Okay, now let's look at B. It doesn't look like this is perpendicular, but I know it is because it's a diameter and it's bisecting a chord. Well, it bisects the arc, therefore I know it bisects the chord. Therefore, I know it's perpendicular to that chord, whether it looks like it or not. So I think I'm going to have to use the Pythagorean theorem. Yep, that's what I'm going to do. This is 5. So I have 5 squared plus x squared. Ugh, this pen. Okay, working again. 5 squared plus x squared equals 12 squared. So x squared equals 144 minus 25, which is 119. So it looks like x is the square root of 119. And oh, now I got to find y. Let me come over here. Let me come to the left. Now I got to use the part times part. So I know that x times y equals 5 times 5, right? 25. Using the theorem that says part times part equals part times part. Okay, so y times the square root of 119 equals 25. So y equals 25 divided by the square root of 119. And of course, we need to rationalize that. Multiply top and bottom by square root of 119. So I'm going to have y is 25 times the square root of 119 over 119. Ugh, what a dreadful answer. But it is what it is. You're going to leave it that way, not turn it into a decimal. So here we go with our last problem of the day. What do we got? You are standing at point Q. So here's you, about 9 feet from a large circular tent. Okay, so you're about 9 feet out there, away from that tent. The distance from you to a point of tangency is 24 feet. So that's going to be 24. Point of tangency. Estimate the radius. Okay, well here's my center. If I draw my radius to this point of tangency, what do I know about that? What do I know about that angle? Hey, I know it's a right angle because I know that any radius to a tangent line, the point of tangency is going to make a right angle. And so what am I trying to find here? The radius. The radius. Okay, so let me Let me just finish that right triangle there. That's R, right? So does that picture make sense? I believe so. Okay, now we got a right triangle, so we could use the Pythagorean theorem, but I want to use the theorem I learned today. I want to use my old friend Al, Al. So let's do that. Okay, so the outside, remember the tangent line there is the outside and the whole. So 24 squared equals the outside, which is 9, times the whole thing. And hey, I don't have the whole thing, right? I have to extend this here to get the whole thing. So what is that whole thing going to be? It's going to be 9 plus 2r, right? Here's the outside, 9. Here's the whole length of that secant, 2r plus 9. So let's see what we got here. I wonder if I can 24 squared. Let me try something here. Uh, let's see, 24 squared is 8 times 3 times 8 times 3. What if I divide that by 9? Just trying to think of a way not to have to square 24. 9, 3, and 3. So I got 64 equals 2r plus 9. So 2r equals 64 minus 9, which I believe is 55. So the radius would have to be 55. What are we looking at here? Feet. I believe that's the correct answer, but please double check me. And you know what? Hey, if you don't believe that ow works, then use the Pythagorean theorem, right? Here would be the Pythagorean theorem if you were going to do that. What would it be? It would be 24 squared plus r squared equals r plus 9 squared, right? So if you don't believe this theorem here works, then do the Pythagorean theorem and see if you get the same thing. All right, that's it for today. We'll see you next time.